we see another one?
Yeah, let's look at this one. We're not going to get, this isn't an initial value problem, but we can still solve this with a couple constants. Many constants do we have? 2, because we got a second derivative. So x plus 2 times y double prime plus x times y prime minus y equals 0. Solved about ordinary point x equals 0. Well, we don't quite have the right format, because we should divide by x plus 2 everything, so that we do this one, but now that means x equals negative 2 is not an ordinary point. Therefore, our radius of convergence, since our ordinary point that's our center is 0, we can't go more than 2 away from that. So this solution is only going to be valid for x between negative 2 and 2. So we're going to assume a solution like this, regular power series, and we can use x equals 0 as the center, right, since it's an ordinary point. And so we'll need a couple derivatives of it. I took the first derivative here, and the first derivative of this, of course, c1 plus 2c2x plus 3, well, same thing I get every time I do a derivative of power series. It's always going to be the same. That's the first derivative, and this is the second. And of course, you know, if we had higher order equation, if we had a third derivative, we could work that out too. It wouldn't be that hard to do. So then we're going to substitute back into this equation. Now this is probably going to be a little bit easier to substitute back into this one than back into this one, the one we've kind of fixed a little bit to put it in proper form to see what was ordinary and what wasn't. So we'll do that, and we'll get x plus 2 times y double prime, and again I'm out of space, so plus what x times y prime, see the original equation, and then minus y, here's that, and that's all equal to 0. So notice, oh, it's tough. This is going to take some thought. But if we started at n equals 2 and multiplied n, that's 2 times 1 times c sub 2 times x to the 1, where do we have that? X times 2c sub 2. See, there it is. And the same thing when we move to 3 times 2, that's 6 times c3 times x to the n minus 1. That'll be this x times this x, so x squared. And I think you can follow that all the way. This term will start at n equals 2, but we'll use the 2 this time. And so we'll say 2 times c2. So that's why when n equals 2, we're going to get x0 for that first term. It's just going to be 4c2. So 2 times 1, which is 4 times c2. And I think you can probably work out that that is like the 2 times y double prime. And okay, now let me see, we got x times c1. How would we write that? Well, n equals 1 times c1 times x to the 1. That's what we wanted it to be. And if you multiply all these out, you can see that they would also work just fine like this. Remember, there's a derivative in there, that's why the n. Remember, there's a second derivative in here, that's why n times n minus 1. Okay, and finally, minus, this is our power series right here, so that's just minus that power series, the thing we said it was our solution. Now, some problems. We need to adjust the subscripts so we have x to the n in each one of these, sorry, this, and this, and this. Problem is we can't add them together unless this was an x to the n and this was an x to the n. So what do? Well, we mess with the subscripts a little bit. We start with n equals 1, and notice it's going to be the same term. This will be still c2, this will be x to the 1, and this will be 1 times 2, so we will still get the same term as if we did n equals 2 on this one, but notice now we got x to the n in our summation. And this one, well, adjust back, just replace n with I guess replace this n with n plus 2 and we would get this, or maybe we should say, well, we want this to be 2 when we begin. The only way that could happen I'm sorry, we want this to be 2, n plus 2 instead of n, so the only way that would happen would be if we kept this 2 here. This n is replaced by n plus 2, but now we start with n equals 0, so that would work out. This n minus 1 is going to be n plus 1, but now we're starting at n equals 0. Remember, if n equals 2, this is going to be 1. Now if n equals 0, this is going to be 1. And if n equals 2, this is C2. If n equals 0, this is C2. So you should realize it's the same, but now instead of x to the n minus 2, I got x to the n. That's what I'm shooting for. I'm trying to get all the exponents the same because I want to combine this all. I want to make this all one big summation. Can't quite do that yet. But one thing I can do, I can say, well, take the n equals 0 term out of this and make it a separate item. Take the n equals 0 term out of this and make it this one and make it a separate item, and then we'll be able to have a summation n equals 1 to infinity for all of them, and they'll all have x to the n as the power of x. So here it is as a single expression. Remember, we took the 0 term out of this one, so that was c0 x to the 0, so there it is. And we took the 0 term out of this one, so that would be 2 times 1, which is 4 times c2. So there that is, and of course times x to the 0. So those two were taken out, but now the rest of this, look, here's this whole thing. This is this part, and now it's all times xn equals 0. So what does that tell us? That tells us that all these coefficients have to be 0, except it also tells us the C2 equals 1/4 of C0. That's from this part. Because this whole mess has got to be 0, so all the powers of x, including the no powers of x, right, x to the 0, have to be 0. So, therefore, we have our recursion relationship right here. As complicated as it is, that is our recursion relationship.
Does it have to take so long?
Yeah, it has to take this long. Sorry about that. I can't see any better way to do it.
You better solve that bad boy.
But we're working on it. So anyway, this is a recursion relationship, and we can solve it for C2, or C sub n plus 2, you know, because this whole thing equals 0. So subtract this and subtract this from both sides, and then divide by 2 times n plus 2 times n plus 1. You can see this is the negative of what I said to do. So there it is, solve for c sub n plus 2. Well, now we got to find our y1 and our y2. And all we have to do is choose c0 equal to 0 and c1 equal to 1, and then c2 equals 1/4, c3 equals negative 1/24 of c, because all I got to do is, for c3, that means n equals 1, put 1 here, 1 here. I said n was, what was it? I forget. C3. This would be like 2 here, so hang on a minute. C3, so n equals 1. 1, 1, this will be C2. If n equals 1, this is 0, C1. So that we won't have that. And n equals 1, so this is 3 and this is 2, so trust me, it does come out negative 1/24. C4, that would mean this would be, n would be 2, so 2 times 3 times C3, which is negative 1/24, and then plus 2 minus 1, which is 1 times Cn, which was negative 1/24, and trust me, I worked all these things out because it was painful not to work them out. I don't know why my software isn't calculating over here for some reason or other, but it did calculate at one time, and I was able to get these just by using a calculator. So hopefully that isn't too awful to see. And so we do that, and then we get our values for c sub I. And once we get C0 equals 0 and C1 equals 1, then C2 is 0 and C3 is 0, and once we got 2 of these equal to 0, then there are always going to be zeros here, and so therefore every other one is going to be 0 except for C1, of course. And so that's kind of nice. So therefore our power series solution is y equals constant times y1 plus constant times y2, And our y1 is this 1 plus a fourth x squared. Remember we found this, and then minus 1/24 x cubed, and then plus 1/480th x to the fifth. The x to the fourth term is 0, so it doesn't show up. This one from here, C7 from here, you can work that all out, it's not that bad. Plus C1 equals 1 times x, or C1, yeah, we said C1 was 1, so anyway, it's C1 times x, and that gives us our two linearly independent solutions. This one for sure converges, right? And this one converges for x between -2 and 2. Now, what does it converge to? We have no idea. It converges to what it is. And so, therefore, if we want a more accurate answer, we just keep going further and further out. So, that's that. And that is the last video.